begin the simulation process by opening the GEDA schematic. Last time we had used the terminal to open, but we could also go into the show applications menu. There is the GEDA schematic startup. Click icon, click on that one. You will have GEDA open up. We have the light background GEDA as we have set it up last time. Use the mouse wheel to zoom in and out dynamically. So first, let us save it as a file that we can name it as rectifier.schematic. So what we can do is go into file, we will do a save as. I have this DC-DC here. I have cleaned up DC-DC, there is nothing else. We can name it as rectifier.sch. So it will be located in that place. Next, we go to the components and try to draw the components from the libraries. So first, let us go and draw the circuit components, which is the diodes, the sources, and the capacitors load. The ACOMS folder library, which we had installed in the last session, contains the generic components. You can use it for most of the simulation because they are generic models. Let us pick the capacitance. We need that. We need a diode, a power diode. We need 4 of them. So let us install 4. I am using ER to rotate the devices. I will rotate this device too. Then we will need load resistance. We will put one resistance here. I will also need another resistance to act as track resistance, otherwise you will end up in convergence problems. So I will place that here. We will see how we will connect it into the circuit. Then we need to draw the source. So the source you can take from the SPICE simulation elements library. The source is a sine source. We will pick a sine source. We also need to pick one more item here. There is SPICE include directory. We need to include a file which contains the library of models, custom models that we would be creating. So we will give a pointer to the file that would be our library, our custom library. Next, we need to take in from the power rails library the generic. This is a generic marking symbol which can pick out the potentials of any points of the circuit. We will keep one there. We need a ground symbol. This is important. Without the ground symbol, SPICE will not work. So I think we have most of them in place. So let us position these elements. So let me put the source here. Let me have a series impedance. This will be a very small impedance. Let us position the diodes something in the form of a full bridge nature. Just position them and then you can adjust it later on like this. Then one more diode. Then we can have the capacitance position like this. Now I will rotate this load resistor and position it like this here. Okay, this we will leave it for now. Now let us draw the wires. The wires can be drawn using this add nets. So click on that. Now you are in the add net mode. You will see that it searches and links to this net. Now I will start putting the wires. Click, right click. Now I will go here, click, right click, click, right click, click, right click. I'm completing the wiring by right clicking. Click, right click, right click, and so on. You make the connection. You make the connection for the diodes too. The diode is a sub-circuit model, that is why we have an X mark, a X at the beginning. All sub-circuits will have X at the beginning. Then the source is connected to the center portion of the bridge, and we have the circuit in place. Change over the cursor. Now the ground, we could probably see, ground is a virtual concept. It is just a reference or the zero node with respect to which the voltages are measured. If we keep the ground here, then when you measure this node, you will get directly the output voltage. If you give the ground here, then you will have to get the output voltage, you will have to take voltage of this minus the voltage of this node. Okay, that is something which you already know in circuit analysis. Now let us place these labels here. Placing these labels are important because when you run the simulation in Spice, the netlist is generated according to the labels that you would provide. If you don't provide the labels, then it will assign some numbers, and then it will be difficult for you to keep track of the circuit node points. If you consciously assign labels, then you will be able to get more insight, analyze, and understand the netlist much better. So let me call this as node A, and I will copy this, paste it, I will rotate it, and I will call this node B. By this, what I have done, I have given a conscious label to this node. Now when I want to refer to the input source, I will say VA minus VB, which will give me the value of the result of that waveform. Then we could give a node number here, and let us say we call this as, and we could give a node for this point. Right. We will call this as E. We will call this as C. We can give one more node here. I would like to place a track impedance here to introduce a non-ideality later on. So for now I will just not give this label. I will remove this label and denote this label as O, so that we know it is an output label. So we have the labels, we have the ground, we have the components in place, we have wired it, we have to give the component names. So So you double click on those. We will call this as RS, series resistance, and it should have a value. And let us not give 100 ohms, it is too much of a series resistance. 0.1 ohm is a reasonable value to take care of the track impedance. We'll come to the source later. We will give names for these diodes. D1, we'll call that D1. We'll call this D2, D4, D3, and the diodes are labeled. Then after that, let us label this capacitance. We'll call it as the filter capacitance CF. We will call this as load resistance. I will call it as R naught. So we will give some value. We could keep this at around 25 ohms so that you see some amount of current. We'll put 1000 microfarad capacitance, like what we saw yesterday, the capacitance value. And now the source, we need to give some value. Let us first give it a name, V in. So we have the name V in, and we need to provide the parameter for the sine attribute. So here we'll have to give the sine wave parameters. When in doubt, you can always refer to the manual. I had recommended in the last session that it is a good practice to download the NgSpice manual and keep it by your side, just to look at the parameters of the sine wave. Now let me go to the manual. This is the NgSpice manual. You see the general syntax: sine, V offset, V amplitude, frequency, delay, and the damping factor. So you can give a damped sine wave also. This is an example of the sine. You have the V in between the positive node and the other node. Sine, 0 offset, 1 amplitude, 100 meg frequency. What we need to give is 0 offset, 3 Vm root 2 or 325, 230 root 2 or 325 volts, amplitude 50 hertz, 0 0. So that's what we will do. So we shall put it as sine. Spice is case insensitive. 0, 325 volts is what we have given. 50 hertz is what we want. No delay and no damping. So that is it. That is source is set. Now to the include directory directive, you make the refdes value 1 and the file. So right now I will type in a file edt01.sub. edt is electronic design technology 01.sub. You can have your own name, whichever is convenient, and close. So it will reflect here, and this is the file that will get included when you generate the netlist. So good time to save the file. Let us close the circuit, the schematic, and now you see that in the DC-DC folder we have rectifier.sch. So we have now the schematics ready, but we have to add 2 more files. One file we will save as into the DC-DC. I will name it as rectifier.cir. Always keep the same name as that of the schematic file name, and only the extension you change it to CIR. Save that. and here first line is always a comment. So start from the second line. We would like to do, we would like to have a transient analysis performed, step time of 50 microsecond up to 100 millisecond using the initial conditions. Also include the rectifier.net. Rectifier for .net is not yet generated, but we will shortly generate that. I will let you know how to do that. So these two control statements for simulation, include it in a separate file, never include it into the net file. It is better if you do it in this kind of an organized way, so that later on for modification, complex simulations, it will be very easy. Save that and close this file. So now you have rectifier.cir also here. One more file we will include. You remember that we had a edt01.sub file which is supposed to contain the models. So let me save this in the same directory, and this time edt01.sub, and save that. So this we have linked in as an include directive. And what should this contain? This is a library of my custom components. So you could have department, Institute, Science, Bangalore. You can have your own thing. Okay, what is it that we need to provide a model? We used a diode there, and it was a power diode. Let us have a model for that. So the power diode is consisting of two parts: a model for the diode, default diode, and the model, sub-circuit model for the power diode. So I think you recognize this. You have the diode between 101 and 102, and you have a resistance, shunt resistance, then again in series with a shunt capacitance. So R shunt and RC shunt are in series and across the diode DX. Okay, so this can be closed, and we have the required files. This is referred already in the schematic. This rectifier.cir gives you what is the type of analysis that you want to perform, and we need now to generate the netlist. So generating the netlist is pretty simple. Open a terminal, and we will go into that folder through the terminal. You see that all these files are there. So let us generate the netlist from the schematic. The command is like this: gnetlist/g spice stb -o rectifier.net. We want the output to rectifier.net from rectifier.sch schematic. So when you run this, it will generate the netlist. So if you look, there is a rectifier.net generated. Now these three files are the ones that will go into NgSpice for simulation. So if you look at the .net, you see the generated netlist, the models taken from the EDT sub. Because of the include edt.sub, you see the V in between A and B. We have applied the labels, and it has taken the label names for the nodes: RS, R0, the power diodes, and the capacitance. Now we just have to simulate. So let us go through the simulation process. You are already in the DC-DC folder. You have to call NgSpice. So you say NgSpice rectifier.cir. You call rectifier.cir because Within CIR, you already have said include rectifier.net, so it will appropriately take the netlist from here. So now you go into the NgSpice environment. So the NgSpice environment has the circuit taken into its memory space, workspace. Run, type the command run, it will run the circuit, and these are the nodes, plot vectors that you will have. What you have to do next is plot. Let us plot V0 or V output. You can always open the schematic for reference. Keep it by your side here. And let us say we want to plot this, plot V0, plot V0. You will see the plot come up. You can double click on that, and then you see the capacitor charging from the startup, and then the ripples as we had discussed in theory. Close that. You want to probably see the source current here. So let us say plot V0, and also I would like to plot the current of which branch? V in branch here, and then you will see that you see the current. Now the current through the source is always considered in the opposite direction, so therefore you see that it is shown minus, but actually the current is flowing in this direction. So whenever you take a source branch, you can give minus of that. Like for example, you can say plot V0 minus I V in. Sorry, plot V0 0 minus I in. So this was the proper direction of the current. You see that initial starter current is higher than the normal steady state current, as we had discussed in the last session.